In this lesson of half-life, we're going to explore what it is as far as radioactive elements or atoms is concerned. And then we shall also look at how to calculate for the half-life of some of the radioactive elements. And of course, determining the amount of element or the amount of radioactive atoms left or decayed after a certain period. So let's begin by defining what half-life is. Now, the word half-life simply means that assuming that we have a radioactive atom and it splits up into two equal parts after a given time period. That time period is what we call half-life. In other words, we define half-life as the time it takes for the number of nuclei of the isotope in a sample to halve. Time taken for the number of nuclei of a radioactive isotope in a sample to reduce by half, to halve. Or we can simply define it as the time it takes for the count rate from a sample containing a radioactive isotope to fall to half of its original level. That is what half-life is. We can look at these examples of these atoms here. For example, uranium-238 has a half-life of 4,500 million years, and very many other radioactive isotopes. So, in case I'm to ask a question here that, for example, the half-life of carbon-14 is 5,600 years. What does this statement mean? It simply means that the carbon-14 isotope, in order for the number of radioactive atoms in that isotope to reduce by half, the time taken must be 5600 years. That is what half-life means. An example is here for the decay of a substance, a radioactive substance or isotope of a radioactive element X. So the question says that the substance X decays with a half-life of 2 hours. What does this mean? It means that, for example, at 2 p.m., there are 6400 nuclei of the substance X. So if the half-life is 2 hours, then it means that, for example, at 2 p.m., the original amount is 6400 nuclei. After other 2 hours, that is from 2 p.m. to 4 p.m., this 6400 reduces by half. In other words, you simply divide it by 2 and you get that as 3200. After more 2 hours, this 3200 reduces by half. You go on dividing it by 2, divided by 2, divided by 2, and so on. Now the question is that when will the nuclei of substance X have fallen to 50 radioactive nuclei? You can pause the video and think about this. I'm waiting for the answer. Okay, so it will have been at 4 a.m. and that is very good in case you've got that answer right. You simply go on dividing by 2 after every 2 hours, 2 after every 2 hours, divide by 2 after every 2 hours until you reach that answer 4 a.m. In other words, whatever remains is this 50 here. So that is what we mean by half-life. Another example is for the substance P. So the question says that if P decays with a half-life of 15 minutes and the original amount at 9 a.m. is 12800, complete the table below. So after every 15 minutes, it reduces by half. Remember that the original is 1280, that is at 9 a.m. So at 9:15, it reduces by half. 9:30 reduces by half, by half, and finally at 10:15, the remaining amount will be 40. So from 1280, the remaining is 40. A question may come that what would have decayed? You simply get 1280 minus 40. Whatever you get will be the one that has decayed. You're going to be seeing such questions as you go on along the way. So half-life is the time taken for the number of the radioactive nuclei to reduce by half. Okay, so a question is here: how many nuclei of the substance will be left at 11 a.m.? Pause the video and try this one out. All right, so you've got the answer as 5. That is very good. Another question, number 2, says that a substance E has a half-life of 3 hours. If at 8 a.m. it has a count rate of 600 per second, what will be its count rate at 2 p.m.? So I've been given the starting time, which is 8 a.m., and the ending time, which is 2 p.m. What is the difference between the two? How many hours are there? So begin by getting the number of hours. So from 8 a.m. to 2 p.m. there are 6 hours left. And if the half-life is 3 hours, it means that we shall be having two half-lives. So you're going to simply divide the 600 by 2 times. So we shall simply have this one as from 600 divided by 2 you get 300. 300 divided by 2 you get 150. So those are the two half-lives, and therefore the remaining count rate will be 150 per second, and that is what we do. Alternatively, you can simply use a table, and you simply say, so we shall have the time and then the count rate. So when the time is 0, the count rate is 600. When the time is 3 hours, the count rate will be 600 divided by 2, that is 300. When the time that has gone is 6 hours now, divide this one by 2, we'll be having 150. And from 8 a.m. to 2 p.m., we have 6 hours. So conclude by saying that whatever remains is 150 counts per second. And that's how we do it. Another example says that the radioactive element of mass 8 grams has a half-life of 8 days. Find the mass of the element after 24 days, and then the mass that has decayed after 24 hours. So the same thing will be done here. We shall simply have that originally we have 8, and 8 divided by 2 gives us 4. 4 divided by 2 we get 2. 2 divided by 2 we get 1. And remember that after every arrow there is 8 days. So 8 days, 8 days, 8 days. When you add up all of these, you go on adding until you reach 24 days. So 8 plus 8, 16 plus 8, that is 24 days. Meaning that our answer, Roman 1, the mass of the element that remains after 24 days is simply 1 gram. And then Roman 2, the mass that has decayed after 24 days will be 8 grams minus 1 gram, which gives us 7 grams. And that is our answer. Alternatively, using a table, you can do this. You can have that we have our mass, we have our time. And originally, if the time is 0 days, our mass is 8 grams. So 8 divided by 2, you get 4. And the time that has gone here is 8 days. Half-life. So plus 8. Then after another half-life, that is 4 divided by 2, you get 2. The time here will be plus 8. That is half-life. You get 16. 2 divided by 2, you get 1. You add on plus 8. So the time here is 24 days. So our answer, Roman 1, is 1 gram. This was in grams. This was in days. And then our Roman 2, you get 8 grams minus 1 gram, you get 7 grams. So that is how we do this. Remember, we can also use an equation, but the equation is not for this level. But in case you want it, you can Google about it. Okay. Example number 2 says that a radioactive element of mass 9.6 grams has a mass of 0.15 grams, and after 24 hours, so we have the original, this is the original, and then this is the final. So the question is saying that determine the half-life. If the time taken is 24 hours, you can pause the video and try this one out. Okay, so method 1, we shall simply say that we have 9.6 grams. Divide this one by 2, we shall get 4.8. 4.8 grams. We're going to continue dividing by 2, until when you get the remaining. When solving these questions here, always look at the original and then the final. That is what is very important in case you don't have the half-life. So 4.8 divided by 2 shall get 2.4. 2.4 divided by 2 you shall get 1.2. 1.2 divided by 2 shall get 0.6. 0.6 divided by 2 shall get 0.3. And 0.3 divided by 2 shall get 0.15 grams. So you have the original, have the final. And where you see an arrow, there is a half-life. T a half. T a half. T a half. T a half. And then finally T a half. How many are they? There are 1, 2, 3, 4, 5, 6. So shall simply say that 6 times T a half gives us the total time as 24 hours. So divide by 6, we shall find that our half-life, T a half, will be equal to 24 divided by 6, which gives us 4 hours. 4 hours. So this is method 1, using the arrow method. Alternatively, you can also use a table. And you say that we have our mass, we have our time. And the mass is 9.6. This is in grams. The time is in hours. So originally, when the time t is equal to 0, the mass is 9.6. So after one half-life, we shall have this divided by 2, which gives us 4.8. After another half-life, we shall get this 4.8 divided by 2, get 2.4. After another half-life, we shall have this 2.4 divided by 2, get 1.2. Then 0.6, that is 4.5, 40 and a half. You go on doing the same. 0.35 t a half, and then 0.15, the final one, you end there. So you have 6 half-lives. And this 6 half-life is the same as 24 hours. So we'll simply come and say that 6 t a half is equal to 24 hours. Divided by 6 on both sides, we get our half-life as 4 hours. And that is what we do here. So the choice is yours. Lastly, number 3. A reductive element of mass 12 grams has a half-life of 7 years. Find the time taken for the element to decay to 0.75. So you must be having the original and the final. So let me use the table. So we have the mass in grams, we have the time in years. And the original mass is 12 grams, the time is 0. So the remaining mass is 0.75. So I'm going to be dividing this 12 by 2 by 2 by 2 until when you reach 0.75. So 12 divided by 2 you get 6, 6 divided by 2 you get 3, 3 divided by 2 you get 1.5, 1.5 divided by 2 you get 0.75, and that is where we stop. That is the final. So the half-lives will be 1 half-life, 2 half-lives, 3 half-lives, and then 4 half-lives. And the question says that the half-life is 7 years. So we shall simply say that our total time, the time taken, will simply be equal to 4 half-lives. And this is the same as 4 times 7, which gives us 28 years. And that is the answer. So a question can come that Roman 2, how much mass has decayed? So simply say that mass decayed is equal to the original, which is 12 minus 0.75, and get your answer as 11.25 grams. That mass decayed. And they can also ask a question here that given that the original mass of a radioactive element is 12 grams and that 11.25 grams decayed. Given that the half-life is 7 years, find the time taken. So what we do in this case is that first of all you must be having the original and you must be having the final. Now if you don't have the final, you begin by calculating that final, that this is the same as from the original minus the decayed. So the original is 12, the decayed is 11.25, the final will be 0.75. And then repeat the same process from the original to the final. Whenever dealing with half-lives, you must be having the original and the final, and then you work on the rest. So that is what we do. Alternatively, we can have questions concerning the graph, and in this case, in case we've been given a graph like this, whereby you have the number of nuclei on the vertical, or you can have the mass on the vertical, and then on the horizontal, we have the time taken. Now, because of background radiation, we said that background radiation always is all around us, and it comes from nuclear reactions, nuclear explosions, it comes from the sun, the cosmic rays, and all radioactive elements around us. So, background radiation is always there. So, because of its presence, our graph never touches the horizontal axis. But in case it does, like this, from this point here to the axis there, in other way, have the 0, 0. In case you have the initial value here, then you simply have to divide this initial value by 2, you get your n naught, divide by 2, and then you follow this pattern here, then down here. Whatever value is here, the half-life, t and half, will always be equal to t minus 0. That is what we do there. Otherwise, this kind of graph may not be practical. So always there's a background radiation. For that reason, the graph never touches the horizontal axis. Now, in that case, what do we do? Like in this example here, what we do is very simple. You simply get any starting value of your own. For example, you can say that your starting value is 400. So you get your 400 as your n naught, then divide that n naught divided by 2, and you get your answer as 200. So from 400, you draw your line to the axis, to the curve, and then downwards. Do the same for the 200. 400, remember you've got 400 divided by 2, you get 200. So from 200, do the same. And then afterwards, your half-life will be equal to, if this is your T2, this is your T1, your half-life will be equal to T2 minus T1. That is how we get the half-life. Now, if your graph has been, if you've been accurate, then the half-life of this is approximately 30 seconds. But in order to get more accurate values, you simply need to get more values where you have different starting values. The n naught one is different, and then you get different values of the half-life, and then you get the average. There you'll be getting the accurate value of the half-life. So that is what we do. Now we have an example here. The question says that from the graph, estimate the half-life of the substance whose decay graph is shown on the opposite side. Pause the video and try this one out. Okay, so in this case, if I take my original as 600 divided by 2, I'll be getting 300. So I draw my arrows like that. And the difference between those two will give me the half-life of approximately 20 seconds. And that is what we do. In case they ask the background radiation, what is the activity of the background radiation? You simply get a line here. So this difference here will give you the background radiation. It will give you the background radiation. All right. So with this, you can try out this question here on your graph. So the count rate of reactive substance over an 8-hour period is shown in the table. Draw a graph of the count rate against the time and use to determine the half-life of the substance. This is for you to try out, and please try it out on a squared paper, on a graph paper. And your answer is that the half-life should be around 2.5 hours. Okay, let's end this lesson by answering these missing gaps here. Choose the words from those ones at the bottom. So, I'm giving some time to think about it. The dash of the reactive substance is the time taken. So what is missing there? Half-life, correct. The half-life of a reactive substance is the time taken for the half-life of the dash of the compound to decay, of the nuclei to decay. Very good. It is also equal to the time taken for the dash rate of the substance to half of the count rate. Very good. Then the half-life of carbon-14 is about 4600 years. Okay, if today a sample of the carbon-14 has a count rate of 3400 counts per minute, then in 5600 years time to come, this should have fallen to, okay, so you divide the other one by 2 until when you reach that time after the 5600 years. So from 3400 divided by 2, you get that there. Then 11,200 years later, the count rate should have fallen to, of course, the remaining answer then is 420. So the number of carbon-14 nuclei would have also decreased by 8 times. Okay, with this, we come to the end of half-life, and I pray that you try out the numbers in the quiz that is next after this video here. See you. Thanks for attending.